In the 20th century, no other invention affected the mankind more than technology did. With the advent of computers in 1950s and internet in 1990s, the fundamental way of doing things has gone through a massive change. These technologies made our lives better, opened up new avenues and possibilities, and gave us a hope for the future. But it generally takes decades for an ecosystem to be built across a particular technology, to take it to masses and achieve the truly disruptive nature of that technology. It is widely believed that 3D printing or additive manufacturing has the vast potential to become one of these technologies. Now, what really is this 3D printing that some have claimed will put an end to traditional manufacturing as we know it, revolutionized design and imposed geopolitical, economic, social, demographic and environmental implications to our everyday lives? The most basic differentiating principle behind 3D printing technology is that it is an additive manufacturing process. And this is indeed the key because 3D printing is radically different manufacturing method based on advanced technology that builds up parts additively in layers at the sub-millimeter scale. This is fundamentally different from any other existing traditional manufacturing techniques. Traditional manufacturing process has evolved a lot over time from hand-based manufacturing to the automated processes such as machining, casting, forming and molding. Yet, these technologies all demand subtracting material from a larger block, whether to achieve the end product itself or to produce a tool for casting or molding processes. And this is a serious limitation within the overall manufacturing ecosystem. For many applications, traditional design and production processes impose a number of unacceptable constraints, including the expensive tooling, fixtures, and the need for assembly for complex parts. In addition, the subtractive manufacturing processes, such as machining, can result in up to 90% of the original block of material being wasted. In contrast, 3D printing process can create objects directly by adding material layer by layer in a variety of ways depending on the technology used. 3D printing is an enabling technology that encourages and drives innovation with unprecedented design freedom, while being a tool-less process that reduces prohibitive cost and lead times. Components can be designed specifically to avoid assembly requirement with intricate geometry and complex features created at no extra cost. 3D printing is also emerging as an energy-efficient technology that can provide environmental efficiencies in terms of both the manufacturing process itself, utilizing up to 90% of standard material, and throughout the product's operating life through lighter and stronger design. In recent years, 3D printing has gone beyond being an industrial prototyping and manufacturing process as the technology has become more accessible to small companies and even individuals. Previously, only big corporates used to own 3D printers, as the scale and economics of owning 3D printer make it prohibitive for smaller companies to own one. But with the rapid decline of the printer cost, the technology has become even more affordable. Nowadays, smaller and less capable 3D printers can be acquired for under $500. This has opened up the technology to a much wider audience, and as the exponential adoption rate continues on all fronts, more and more systems, materials, applications, services are emerging. In the coming lectures, we will discuss about various 3D printing processes in greater detail. The entire 3D printing technology can be divided into three steps: 3D design, slicing, and 3D printing. 3D digital model is the starting point for any 3D printing process. This digital model can be created using various 3D design software like Fusion 360 and SolidWorks, or can also be created using 3D scanning. Once the 3D model is created, it is then sliced into layers, thereby converting the design into a file readable by 3D printer. This slicing is done by exporting 3D model to another software like Ultimaker Cura. 3D printer will then print this file layer by layer using the material given as input. The different types of 3D printers each employ a different technology that processes different materials in different ways. It is important to understand that one of the most basic limitations of 3D printing in terms of material and application is that there is no one solution fits all. For example, some 3D printers process powdered material, which utilize a light source to sinter or melt layers of the powder together in the definite shape. Other process requires polymer resin material and again utilize a light or laser to solidify the resin in ultra thin layers. Now, let's discuss about some of the very famous 3D printing processes. First is SLA or stereolithography. Stereolithography is widely recognized as the first 3D printing process. It was certainly the first to be commercialized. SLA is a laser-based process that works with photopolymer resins that react with the laser and cure to form a solid in a very precise way. It is a complex process, but simply put, the photopolymer resin is held in a vat with a movable platform inside. A laser beam is directed in the XY axis across the surface of the resin, according to the 3D data supplied to the machine. This 3D data is in the format of .stl file, whereby the resin hardens precisely where the laser hits the surface. Once the layer is completed, the platform within the vat drops down by a fraction in the Z axis, and the subsequent layer is traced out by the laser. This continues until the entire object is completed and the platform can be raised out of the vat for removal. Because of the nature of the SLA process, it requires support structures for some parts, specifically those with overhangs or undercuts. These structures need to be manually removed. In terms of other post-processing steps, many objects 3D printed using SLA need to be cleaned and cured. Curing involves subjecting the part to intense light in an oven-like machine to fully harden the resin. Stereolithography is generally accepted as being one of the most accurate 3D printing process with excellent surface finish. However, limiting factors include the post-processing steps required and the stability of the materials over time, which can become more brittle. DLP or digital light processing is a similar process to stereolithography in context that it is a 3D printing process that works with photopolymers. The major difference is the light source. DLP uses a more conventional light source, such as an arc lamp with a liquid crystal displays panel, which is applied to the entire surface of the vat of photopolymer resin in a single pass. This generally makes the DLP or digital light processing faster than stereolithography. Also, like SLA, DLP produces highly accurate parts with excellent resolution. But its similarities also include the same requirement for support structure and post-curing. However, one advantage of DLP over SLA is that only a shallow vat of resin is required to facilitate the process, which generally results in less wastage and lower running costs. The next process is laser sintering. Laser sintering and laser melting are interchangeable terms that refer to a laser-based 3D printing process that works with powdered materials. The laser is traced across a powder bed of tightly compacted powdered material, according to the 3D data fed to the machine in the XY axis. As the laser interacts with the surface of the powdered material, it sinters or fuses the particles to each other, forming a solid. As each layer is completed, the powder bed drops incrementally and a roller smoothens the powder over the surface of the bed prior to the next pass of the laser for the subsequent layer to be formed and fused with the previous layer. Once finished, the entire powder bed is removed from the machine and the excess powder can be removed to leave the printed parts. One of the key advantages of this process is that the powder bed serves as an in-process support structure for overhang and undercuts, and therefore complex shapes that could not be manufactured in any other possible way can be manufactured with this process. However, on the downside, because of the high temperatures required for laser sintering, cooling times can be considerably high. Furthermore, porosity has been an historical issue with this process, and while there have been significant improvement towards fully dense parts, some applications still needs infiltration with another material to improve mechanical characteristics. 3D printing utilizing the extrusion of thermoplastic material is easily the most common and recognizable 3D printing process. The most popular name for the process is fused deposition modeling. The process works by melting plastic filament that is deposited via a heated extruder, one layer at a time, onto a build platform according to the 3D data supplied to the printer. Each layer hardens as it is deposited and bonds to the previous layer. The most common material for entry-level FDM 3D printers are ABS and PLA. The FDM process requires support structures for any application with overhanging geometries. For FDM, this entails a second water-soluble material which allows support structures to be relatively easily washed away once the print is complete. Alternatively, breakaway support materials are also possible, which can be removed by manually snapping them off the part. The process can be slow for some part geometries, and layer-to-layer adhesion can be a problem, resulting in parts that are not watertight. Again, post-processing using acetone can resolve this issue